9:30, folks. Let's get this show on the road. So last time we got together, I talked about optoelectronics, and I had that little display where I had the fan and the phototransistor, and every time the propeller blade would break the laser beam, we would time the pulse train, and we got the RPM of the blade. Cool. We're going to build on that idea today as we talk about measuring rotational speed. And typically in machinery, rotational speed is measured with something called an encoder. An encoder can be either relative or absolute, and they kind of overlap a little bit, and you'll see what I mean as we go along in this lecture. Encoders, what do they look like? Well, they look like that little silver can right there. They come in all different shapes and sizes. This is the one I'm going to demonstrate. So as usual, I've got a little demonstrator model right here. This is exactly what's inside this. And in fact, I've even got it programmed with the same software, just so you can see what's inside the box. So when you have a control system, a lot of times you're going to send a command to a motor, a power stage, something like that, and you've got to say, did it actually happen? Okay, feedback. That's what your encoder is all about. So for example, if I say I want a stepper motor to move one click, I can use an encoder to check that I actually got one click of revolution on my stepper motor. And if I don't get that within a certain time, I can throw up an error signal and say, hey, warning, something's jammed. Operator, intervene. So the basics of an encoder. You got a little phototransistor, just like we had with the fan. You got a slotted disc, and you got a light source. Laser, LED, white light, don't care. Some light source. So as that wheel turns, the phototransistor is going to be switched on and off, and you'll get a square wave pulse train coming out. And if I have just one of those, so for example on this thing, if I had just the outer set of slots, okay, just like with a fan, I can get speed. What I can't get is direction. So if I want to know, is my motor oscillating? Or am I turning forward? Am I turning backward? What's going on there? Okay. I've got to have two sets of slots. And that's what's going on in my little demonstrator rig. So with one set of slots, I can get speed. With two sets of slots, I can get speed and direction. And you'll notice that they don't line up. And there's a reason for that. These slots are exactly 1/4 of an interval staggered. It's called quadrature codes. All right, let's see if it makes me log in.
Hi students. Today I'd like to introduce you to a motor control device called an encoder. In front of you is a small DC brush motor. That's the cylindrical section right here. And below is the optical encoder. The encoder puts out a set of 0 to 5 volt pulses as the motor spins. So every revolution of the motor outputs 500 pulses, and it can be more or less depending on the model of the encoder. Let's start this up and look at the output. So you'll notice that there are 3 pulse trains. The first one is called the sync pulse, or the home pulse. That pulse occurs once per revolution of the motor shaft. Below that are the phase A and phase B encoder pulses. And what I want you to notice about these is they don't line up. So if I look at, say, this edge and this edge, they're off by exactly 1/4 of a pulse cycle. That's called quadrature. And what we can do with that is determine the rotation direction of the shaft. So if I take any two slices, and by that I mean big slices, so a high and a low, then come over a little bit, low, low, and I do an exclusive OR logical function on those pairs of bits, then the exclusive OR will give me either a 1 or a 0, and that determines the direction of the motor rotation, either clockwise or counterclockwise. Another thing I'd like you to notice is that these are 50% on, 50% off pulse trains. So these are not pulse width modulation. Don't get the idea that as I speed up, the duty cycle is going to change. And in fact, let's watch what happens. I'll increase the voltage to the motor. And you can hear the motor pick up speed, and you can see that the pulse width got narrower, but it's still 50% on, 50% off, and the two pulse trains are offset by 1/4 of a pulse. So if I increase the speed fast enough, we can actually get 2 sync pulses on the screen. So voltage is going up, going up, going up. And I'll increase the number of seconds per division. And there we go. So you can just see that I have the sync pulse here that I'm triggering on, and the second sync pulse is here, and I have 500 pulses between this trigger point and the next sync pulse. So the quadrature controls, or rather indicates the direction of rotation. The pulse width indicates the speed. And by using the 0 reference or the sync pulse, then you can actually control position of the rotor shaft. Very neat little device. So, hope you've enjoyed this, and thank you for watching.
Okay, so, cutesy little demonstration. Not a super hard concept, guys. Every programming language has exclusive OR built into it. So you don't have to worry about putting logic tables in your software or any jazz like that. You can just use the command, and I will show you the software that's running that in just a minute. So I data logged the output from that video, and there it is. So you can see phase A, phase B, and you can see the 25% offset. And this makes it a little bit bigger and clearer. Yes, in fact, it is a 50% duty cycle. It's just slightly skewed on the time axis. So I think we've already kind of beat this to death. So you can slice this up. And when you do the exclusive OR, folks, so on every interrupt, every change of channel A and B, I were to write down the state of that pin, and then I come in here and I look at phase A and B for any two pairs. If I take phase A current state and the phase B from the previous interrupt, and I do the exclusive OR, that's how I'm getting my direction. So you got to look back one interrupt step to get your direction. And on the Arduino, it's as simple as this command right here. So what looks in Excel like an exponent function is actually exclusive OR in the Arduino C programming language. So the software I've got going into my little demonstrator, I've got my channel A pulses coming around here. I've got 5 slots, another 5 slots, equal angle, but offset by 25%. I've got my light sources for my phototransistors down at the bottom. Every time one of these little windows pops up, the phototransistor becomes conductive. It allows the input to go low and triggers an interrupt on the Arduino. And if I reset my Arduino, I do have a problem. This was running perfectly on my kitchen table last night. For some reason, it's going to 0 on startup. If you start your encoder, an incremental encoder, you have no idea where it is until you go around and you hit that first sync pulse. Then you can start counting and get position. Okay, so I was stuffing some bad data in there. I was calling it step like 3,000, 2,999, just to visibly show, okay, the data's bad. I'm not within the range of my number of pulses. But as I rotate the wheel, you can see it does in fact count right up until, so my sync pulse is coming around. The sync pulse fired, said, oh, 0, I'm at my home position. Then as I continue rotating, the values get more and more negative until I go around to the sync pulse again. If I go the other direction, you can see it changes from counterclockwise to clockwise. That's that exclusive OR function. And it counts up right until I go past the sync again. Okay, so pretty neat. We already went through interrupts. I think I've kind of beaten that to death. Does anybody have any question on what those are? So you can set up a pin. When it changes or there's an event on the input, it just runs off and automatically does some subroutine that you've predefined. That's really all you need to know about microcontroller interrupts. But there are times when you just can't tolerate that. Okay? You've got to know where that rotor is every second, all the time. So if I've got a welding robot that's reaching down inside the frame of, a $2.5 million Ferrari, and there's a power glitch, and all of a sudden my machine loses its home, the last thing I want to do is just say make a random move and risk ripping through the frame of that $2.5 million Ferrari. That's where your absolute encoders come in. And they are a different beast entirely. Not entirely, but significantly. So conceptually, we can think of them as just a bunch of binary numbers cut into a disk. You guys, have you experienced binary numbers? You know what binary numbers are all about? I'm seeing a few head nods. Okay. So let's imagine that we're going to make an encoder wheel, and we're going to make a 3-bit encoder wheel. So that's going to be 3 circular tracks. If I have 3 bits, I can go 2 to the 3rd power. I can do 8 wedges. on that encoder. So it's going to be a 45-degree increment. In the first one, for position 0, I'll have 0, 0, and 0. No rocket science there. If I take 2 to the 0th power, I get 1. If I take 2 to the 1 power, I get 2. Da-da, da-da. Okay. And here's how you go from base 10 to binary, or from binary to base 10, I should say. Okay. And if you do that, and you work your way around, graphically you get something like this. And you know, we could do a little machine design on this, and we could actually cut this into a metal disc. We could put 3 photo transistors on there and have 3 data lines coming out. And at any point, we would know which arc segment we're in. But there's a problem. And the problem comes right at the value of 3. The problem you run into is that you've got two tracks changing simultaneously. And what that's going to do is when the microcontroller sees that, it's going to say, which interrupt routine do I service first? Okay. Or you could get into something of, maybe there's a slight variation, phototransistor to phototransistor. One of them fires before the other. Okay, what do? We have a way around this. And instead of actually cutting binary numbers into our encoder wheel, what we're going to do is we're going to use something called gray code. Okay. Guys, gray code, I looked and looked for a really good, easy way to describe this. But just think of it as binary numbers, same number of ones and zeros for any given number, but the key difference is that only 1 bit changes from number to number. So if you go from 2 to 3, only 1 bit changes. If you go from 37 to 38, only 1 bit changes at a time. So that creates only 1 interrupt firing on your microcontroller, and you can actually track what is changing without running into weird ghost issues and potentially 1 interrupt being missed or something like that. And this is what a gray code absolute encoder wheel actually looks like. So it's 12-bit. That means you have up to 2 to the 12th power division of an angle on this thing. And there you go. So if I take any one slice and go 4096 the way around, there's only 1 bit changing as I move along the arc circle. So of course, got to have a demonstration. I'm all about the demonstrations. So we'll pull this one aside. I'll do the other one real quick. Let me just jump back to the concept of incremental. Okay, so that little homemade encoder that I had on the table, that is exactly the same as this industrial version. This is 100 pulses per rev, and this one didn't have the little bug that I ran into with the sync pulse on the other one. So if I reset the encoder, I get my junk value, 2,999. I know something's wrong. I'm out of range. This is a 100 pulse per rev encoder. So if it's saying 3,000, I know I'm bad. But as I rotate this thing, so I'm rotating it clockwise, my numbers are increasing right up until the flat is on the top, or the cables come out on this one. Bang. So I hit the sync pulse, I reset to 0, and now I'm counting forward, and it's 100 pulse per rev. So as I go all the way around, come around to 93, 97, 98, 99, 100, bang, back to 0. And I go the other way. I programmed it to go negative. I could have just as easily written the code to say, okay, if I'm going forward, count up. If I start going backward past the sync pulse, okay, set it back to pulse 99 once you go past sync. That's just a programming thing. Okay, so this is the industrial version of that. Let's jump into absolutes. This, on the other hand, is an absolute encoder. And I'm going to need a little more computational horsepower to read this thing. And I posted all of the driver files and software that I wrote for this demo. So if you're really geeky like me and you want to read it and look at it and see how I did it, it's all there. Or if you want to use it in your mech lab in some way. So for this demo, what I did is I took the Crosby machine controller. I added a couple little bells and whistles. I added a gray code decoder to it, which you might want to check out. See how easily she's going to hook up to that. Now we're talking. For this particular model of encoder, I had to actually light up the internal LEDs with a 12-volt power supply. But immediately, as soon as I lit up the power, it knows the shaft angle. 222.20 degrees. I'll rotate it around. So now it's at 18.28 degrees. If I cycle the power, I lose everything, but the minute I put it back, 18.28. It's slightly harder to hook up an absolute, folks. So this is an 8-bit encoder, which means there are 2 to the 8th power divisions in this encoder. That means it's dividing up the circle into 256 individual pi wedges. And to get that data out, I had to take 8 data lines out for the 8 bits of the encoder. And those are going to port L on this Arduino. That's getting a little bit more advanced than we need to talk about for this class. But just know that if you're going to deal with an absolute, you got a whole lot more data lines going out than you do for a simple incremental encoder. Okay? The rest of it, pretty much self-explanatory. So the phototransistors bring the data in inverted, which I then have to convert back to actual gray code. The slick way to do that, if you have to change all of those pins, if you do an exclusive OR with one, the bit 1, okay, that always flips the bit. So I ended up doing an exclusive OR with whatever's coming in with 11111, 255, and that flipped all the bits in one command. So that was quite nice. Then I sent it to my gray code decoder. It swapped the bits around. You can see the gray code is just ones and zeros, just like the binary. And then from there, converted to an integer and an angle. Not a lot of rocket science. We'll skip this one. And if you really want to geek out, and you really want to understand the binary to gray code and back and forth conversion, I found somebody on YouTube, because you can learn anything from YouTube. You can watch this, but I'm not really going to go over it. As long as you understand that gray code is like binary, but only one bit changes as the numbers go up or down, cool. For a Mechie, that'll get you by. So next week, we have your second lab report coming due. I'm going to be out the rest of the day today. Tomorrow, Thursday, and Friday, I'll be in Crosby all day. If you run into any issues, if you need any hardware, whatever the case may be, feel free to stop in. I don't have anything except maybe a tour on Friday at noon, and we're good. So this next report, you will pass it in. I'll give you a grade on it, give you feedback. You'll have a chance to do a rewrite, resubmit it. Hopefully it comes back a whole lot better. And that's it for the course, guys. And we'll keep talking about different sensors. We'll do PID loops, and we'll do other stuff as we go through the rest of the course. That's all I got. Thank you very much.